Okay, so today our speaker is Shai Genel, who is visiting from MPE, not MPE, where he's working with Reinhard Genzel and Forsino and finishing his PhD, which he will finish this winter. And he's going to talk today about load of red triangles also and formation of redshift galaxies.
Thanks a lot. Thanks for being here. Thanks for having me. So, yeah, I'm going to talk about my work in the past 4 years in my thesis. So, indeed, with my supervisor, I'm a dancer at the beginning of the group, in collaboration with folks from the University Observatory of Munich, and Nicolas Boucher was at MPE and now in Santa Barbara, and Hans Kerber from the University. So, my talk is going to be divided into two parts. In the first part, I'll discuss dark matter halos, merger rates, and in general, the growth of dark matter halos. And in the second part, I'll discuss cosmological hydrosimulations of redshift star-forming galaxies, give some observational background, and then discuss simulations. So, motivation for the first part of my talk is that structure in the universe grows hierarchically, so halos start forming from small to very large cluster halos that we see today, and galaxies form in the center of the halos. So one thing we may want to understand before we understand galaxy formation is how dark matter halos grow, and this is actually much easier to understand. So I'm going to try to address some aspects of that question. And I've done that with the Millennium Simulations. These are two antibody, cosmological antibody simulations, each of which has 10 to the 10 dark matter particles. And the first Millennium simulation from 2005 was in a box of 500 megaparsecs size, quite large cosmological volume. That means that the mass resolution was, so the smallest resolved halo was about 10 to the 10 solar masses in the first Millennium simulation. The second Millennium 2 simulation from last year had the same number of particles, but the box was 5 times smaller on the side. That means the mass resolution is 125 times better. So the smallest resolved halos we have are about 10 to the 8 solar masses. So after the simulation was run, first step in order to quantify the growth of structure is to identify structures in each snapshot of the simulation. So this was done in 2 steps. First step was running the frames of frames algorithm on each snapshot of the simulation. This algorithm creates what is called frames of frames or folk groups. Each group, so on average, those groups have overdensities which correspond to the overdensities of realized objects. So those structures, frames of frames groups, are more or less considered as realized dark matter halos. So this is an example for one such a folk group. We see that it has some background and lots of substructures. So those substructures are not captured by the folk algorithm, which just puts it all together into one group. So then came the second step, which is the subfind algorithm, which was run on each folk group. And basically it identifies density maxima in the folk group and bound particles around each such maximum. So for example, in this folk group we have the main subhalo, which is sometimes referred to as the background subhalo, and all the other 55 subhalos, and also some fuzz of unbound particles, which are then not considered to be part of the halo anymore. Okay.
Velocities are too high.
Right.
You don't stay in the halo, but you check this and the particles leave.
I'm not sure, I'm not really aware of whether people are really looking at the history of those particles. This is basically done in one snapshot, not following their history, just based on their energetics. But it's interesting one. Okay, so now these substructures are followed between snapshots by just looking at the particles that belong to each such subgroup, looking at the next snapshot, identifying the particles there, and creating a descendant, a subhalo descendant for each subhalo. And so a merged tree of subhalos has been built. So based on those descendants of the subhalos, one can build then a merged tree of the full dark matter halos, and this is in principle easy to do. So in this example, we have two halos merged together. One of them becomes a subhalo inside the big one, and now if the subhalo is still surviving inside the big halo, both the descendant of this one will be this one, descendant of this one will be this one, and we can just put the box here represent the full halos or the four groups. So the descendant of this four group would be just this four group, and it all makes straightforward. The problem is that this is not the case because sometimes substructures which are in the same four group turn out to be belonging to different four groups in the future, in some future snapshot. So the question is, so what do you do here? What is the descendant of this halo? This connects to the well-known fact that the Fourth algorithm sometimes can artificially connect halos. Basically, so the Fourth algorithm works in a way that it finds neighboring particles and puts them together in the same group. So you can, there could be like a thin bridge of particles connecting two halos that will put them together in the same Fourth group. And so by looking at those cases, I arrived at the conclusion that actually most of these cases where you have two structures which are connected together and then later split are actually artificial and they're far from being realized at this stage. So the solution then was to just, in each such case, I already here at this stage, I split those two substructures and I regard them as two independent halos. And so basically, I just look, I consider them being merged just at the last time that they merge, after which they never separate again. An alternative solution, which
how do you know they won't separate again?
Sorry?
How do you know they won't separate again?
Yeah, so basically it's just, I'm looking at all the snapshots shots of the simulation. Of course, when I'm close to H0 and the simulation just stops, then I start losing this information, and I know that close to H0 I have such cases which, some of them statistically, I know that will separate in the future. So indeed, my analysis is basically based on analysis of redshift higher than 0.3 or 0.5. After that, I I know that I'm doing it.
The binding energy should tell you, presumably, the subject will escape or not, right?
Right. I mean,
if it's not actually from that object, right?
Right. So you
don't use that though.
Right. Okay. So I just use the subject of my trees. So we could do most of these things. But yeah, because but I mean, then you get more complex criteria. I mean, there have been people who did similar things.
Subtype already is very complex, right? Right. So this doesn't seem like so much over there.
What was important, so other people have done things like splitting halos based on velocity considerations and so on. But what was important for me to do is to use the merger trees in order to never count a merger more than once. So in this, so what has been done in the literature before is basically snipping one of the pairs. So basically taking the bigger one here and putting that one as the descendant of this artificially joined group, and then this smaller one has no progenitor, which means that we actually see two mergers. Those two same structures merge once here and then they merge again here. And I really wanted to avoid anything like that, so that's why I just based my analysis on the merger trees. So even if I used more additional criteria, I would still not be sure that close to H0, I may still have cases that are artificially connected. Okay. So once I've done this splitting and connecting descendant for each halo, then I have merged trees of halos, and then I can just look at those those trees and measure the merger rate of halos from the trees. So what I'm going to, the quantity I'm going to show you is the merger rate per halo. So each halo, the rate one halo undergoes, so not per volume, per unit redshift, per unit mass ratio of the merger. And this quantity is a function of the mass ratio of the merger, the redshift, and the mass. And as also Kahoot showed, this quantity has quite a simple, can be fit by quite a simple formula with also dependencies on these three parameters which are separable. So I want to describe now, I'll show you the dependence on each of these parameters. So first we see that there's a weak mass dependency. This shows the merger rate per descendant halo, this quantity, as a function of mass ratio of the merger. These are major mergers, these are minor mergers with large mass ratios. This is at a given redshift, just for example. And here in green are halos of 10 to the 14 solar masses, and in black 10 to the 10 solar masses. So this spans 4 orders of magnitude in halo mass, but only a factor of 4 in the merger rate. So higher mass halos have higher merger rates, but the dependence on mass here is pretty weak. So the alpha, the index here with the power law of mass is only 0.1. So this is as a function of mass ratio, and it's higher here at the major merger regime, just because it's defined to be, the quantity is defined to be per unit mass ratio.
So what's M star?
Sorry?
What's M star for this view of 1? So it's like the characteristic nonlinear mass scale, I guess, like kind of like the, no,
Well, yeah. Yeah. More than that?
Yeah, okay, so 10 to the 14 is unreasonably rare.
Yeah. Yeah, it's one. Yeah, so this is shown, these are the results from the both simulations. So basically, the circles here show the results from Millennium 2. You can see that for 10 to the 14 halos, it stops here. There are basically not enough statistics to probe major mergers of 10 to 14 halos in small ones. Okay, so this plot shows the cumulative number of mergers as a function of mass ratio. So in blue here, we see for 10 to the 12 solar mass halos in redshift 2 that there are also only 0.3 mergers per gigayear when you consider mergers with mass ratio of 1 to 3, so major mergers. While if you look at mergers with mass ratios of 10 to like 1 to 1,000, for example, you see 10 mergers per gigayear. So there are many more minor mergers.
Where's the mass? All major mergers?
Sorry?
Where's most of the mass coming from?
I'll discuss that in a minute. Most of the mass is coming from the I'll show you. Then the redshift dependence is strong. It goes about 1 plus z to the power of 22. This is faster than the evolution of the Hubble time. So in blue here, we see the major merger rate per gigayear for this halo mass as a function of redshift. So we see that at redshift 0, we have only 0.03 mergers per gigayear. That is, the typical time between major mergers is 30 gigayears. But at redshift above 2, this typical time between major mergers becomes shorter than the ages in meters.
Is there a difference between Millennium 2 and Millennium 1?
They agree perfectly where they overlap. So this is again as a function of mass ratio. In blue here is the same curve I showed you before. These other curves show you what happens if mergers, if the splitting algorithm is not implemented. And mergers are then counted sometimes several times the same merger. And this happens more at minor mergers, when small things come in and out of the halo a few times. This inflates the minor merger rate, as you see here. And I'll discuss in a moment the important implications this has for the general growth of dogmatic halos.
Sorry, these are tree algorithms that build trees from a legacy.
Yeah, so these are all based on the same sub-halo trees, but just doing different things in how to create full halo merge trees from the sub-halos.
So I don't know, why is it that you find fewer, maybe minor mergers than the whole GML.
So the reason is that the different algorithms from Millennium allow sometimes for, say, a high mass ratio mergers or minor merger, for the small thing to come inside the halo and merge, and then split out of the halo without being really accounted for. And then it comes back again and counted again as more or less the same mass ratio merger.
So you count them twice.
Yeah, so simply, I don't want to go into this, but I could find this table in my paper where the different algorithms and different cases of how long the halos come in and out, and what's the time difference, how long they spend out and in again, and so on. So, and the different algorithms treat these different cases differently, but all of them, except from what I showed you in the beginning, there are cases where they count the same merger more than once, and that's why you get this higher.
Looking at deviation, it looks like it counts many times, right?
Sorry?
After 3, it looks like they're going
Yeah, this happens many times.
So if orbits, they just go outside the real ring, so they just count it again and again and again, and that happens.
Okay. One more point that I want to make is that I showed you until now the merger rate per descendant halo, but you can also define the merger rate per progenitor halo. The merger rate per descendant halo relates to the probability that a halo you're looking at has just been formed, has just undergone a merger. The merger rate per progenitor halo is related to the probability that the halo is just about to encounter a different halo. Usually these are exactly the same thing, but in the regime of very rare halos, these are different things. Because if you consider a very rare halo at a high redshift or high mass, it's much more probable that it has just been formed by a major merger rather than that it is just about to encounter a rare halo like itself. So the merger rate per descendant halo that we discussed so far is monotonically increasing with mass and redshift, while the merger rate per progenitor halo actually has a peak. So this is the major merger rate as a function of mass for the redshift. So you see that, so this is per descendant halo, while for progenitor halo already at 12 solar mass halos at redshift 3 is rare enough so that the merger rate starts being lower for higher mass halos. The same is true as a function of halo mass at low redshift. This is for descendant halo in the blue, here peaks for progenitor halo. Now these two definitions correspond to the two different methods with which observers try to measure the merger rate with merger fraction, which is, so per descendant halo corresponds to identifying structural disturbances, asymmetries, and so on in galaxies that have already undergone a merger, as opposed to measuring the pair fraction, which is measuring the mergers which are just about to happen. So while there's still a large scatter in the observations of the merger rate, and since this is important for rare halos, this has not been yet seen observationally, but just want to make the point that these are actually two different quantities, and they should not equal each other, even after you take into account the time scale issues. Okay, so I want to go back to the growth of dark matter halos. So I've discussed mergers so far, but dark matter halos in the simulation grow also by accreting just single dark matter particles, which do not come as part of smaller bound substructures. So this shows the fraction of the growth rate of halos that comes from resolved mergers as a function of halo mass, and this is shown by the red curve. So at low mass, we just cannot resolve very high mass ratio mergers. So naturally, most of the growth comes from accretion of single dark matter particles. This is a resolution. But what's interesting is that as we resolve halos better and better, and for the best halos we can resolve with mass ratios of 10 to the 5, we still see that the mergers contribute only about 50% to the total growth rate of the halos. So you see this.
So this goes to mass ratios of
10 to the 5.
100,000.
Yeah. So this is the best that we can really resolve with the simulations we have. And
Fraction of mass in lower mass guys, because I guess logarithm, right, like mass function was like 1/x squared, right? Yeah. So as you increase the resolution, your ability to find new like converters only goes up, like the log, right?
Right.
Yeah. So your statement that it converges like can't ever be validated, right?
Can I understand?
So you can't actually say that the merger rate has converged, right?
So, okay, so the power law of the merger rate that I find is actually, well, it's higher than -2. It's about -1.8 or 1.7. And this is exactly the point where it's very important, where it's very sensitive to the exact algorithm of building the trees. So indeed, if I extrapolate the fit that I found for the merger rate, this does converge on about this value of 50 or 60%.
So there's 1.8, let's say, right?
Sorry?
So the slope is like 1.8, let's say,
Yeah.
right? Yeah. Then as you increase the resolution and the fraction of mass, that you're getting in mergers is only increasing like the 0.20 power of your resolution, right? And so then how can you say with any confidence that you converge?
Well, what I'm saying is that if this power law holds for higher mass ratios, then
Which you don't know, right?
which I don't know, of course.
Right, yeah. The mass function itself behaves just like one of the mass squared, basically. Masses. And so we'd expect this thing also to scale the same way. Right?
Yeah. I mean,
it's a minor point, but it doesn't seem like you can actually say this is converged.
No, definitely, I cannot say, but what it's interesting why there is this difference. I mean, it's a small difference, but this difference between -2 and -1.8 is exactly what's important. So if it changes, if it changes even here, around here, where we cannot resolve any better, to -2, it will still not be enough to for the contribution to go to 1. So we really have to change rapidly or strongly to compensate for all the errors. This has, so actually 2 weeks ago there was a paper on SFRS from Wang et al. Where they looked at the Aquarius data, so a sample of just 6 very high resolution zoom-in simulations, and where they have resolved mass ratios of 10 to the 6.5, so 1.5 orders of magnitude better than what you can do with the big box, and they actually arrived at a very similar conclusion. They see that about, so, I mean, okay, definitely, I mean, you can never really count on an extrapolation. You don't know what happens where you don't resolve, but what I want to say is that maybe it doesn't matter that much for galaxy formation. And the reason is that with the Millennium 2, we already resolve halos of 10 to the 8 solar masses, which have virial temperatures of above 10 to the 4 Kelvin. So even if the rest of the mass comes not really smoothly in dark matter, but in smaller halos, those smaller halos will have real temperatures of less than 10 to the 4, which means that maybe they don't hold their cosmic share of gas. So maybe indeed 50% of the baryons come into halos smoothly, regardless of what's happening in the smaller halos, which we cannot resolve right now. Okay, so to summarize the first part of my talk, merge tree construction algorithm is important, especially for the smooth accretion. The merge rate has a weak mass dependence, but a strong redshift dependence. By number, most mergers are minor, but by mass, most of the contribution from mergers comes from relatively major, so 1 to 10, 1 to 100 mergers. But there's a large contribution that seems to come from very smooth accretion. And one should in principle distinguish between merger rate per descendant and per progenitor. So to the second part. talk. I ask some questions now. Okay, so I'm going to give a short observation introduction to redshift 2 star-forming galaxies. So this plot has become quite famous over the past few years. This is the star formation rate versus stellar mass of galaxies. And all the points here in black show redshift 2 galaxies. We see that there's quite a tight correlation between the quantities, and they are more or less, so the star formation rate is more or less proportional to the stellar mass. And this correlation actually appears at lower redshift 2, not only at higher redshift 2, not only at redshift 2. So the blue lines here show you the mean of the same correlation at lower redshift. This is redshift 0.1, this is redshift 1. So you see that this correlation evolves strongly with redshift. If the Milky Way is more or less here, then the galaxy with the mass of the Milky Way at redshift 2 forms stars at about 100 solar masses per year. In the local universe, we have such high star formation rates just in merger-induced starbursts. So a natural thing to suggest was that all these galaxies at redshift 2 were mergers, and we also know that the merger rate increases with redshift, but this seems not to be the case. So if we resolve those galaxies, we see, first thing we see about them is that they're very irregular and clumpy. So again, I mean, maybe this is just a merger of many galaxies. So we have, I want to show here two lines of evidence why this is not the case. So first, this is the same galaxy in two different bands. This is in the rest frame UV, and this is in the rest frame optical. It's probed by in the Z band and H band. So we see that, and this is a general trend, that in bluer bands, those galaxies are more clumpy. In the rest frame optical, which traces more of the stellar distribution, they're not much more concentrated. So if these were incoming mergers, small galaxies, you would expect in the stellar distribution not to be so deep to see those clumps in the stellar distribution too. The second argument was made by Green in 2005, where they tried to assign an aspect ratio to those galaxies. So here, for example, we see a chain galaxy, an elongated galaxy with a few clumps. So, and the distribution of the aspect ratios between the clump cluster galaxies and the chain galaxy is actually consistent with them being the same kind of galaxies, but just seeing more face-on and more edge-on. So these may be just disks, so clumpy disks. Another evidence for that came from the SINS survey led by the infrared group at MPE, where those galaxies have been observed with Symphony, which is an integral field spectrometer. So we probed there the H alpha line, which probes star formation. This is in the rest frame R band. And the galaxies are spatially resolved. So in each pixel on the image of the galaxy, we have the full spectrum in the H band or K band, where we have the H alpha line. So we see the position and the width and the intensity of the H alpha line. So then we create these kind of maps: line intensity, velocity, and velocity dispersion maps. And what we see here is that in many, so there's a large population of those galaxies which are, first of all, extended. This line here is 8 kiloparsec. And the velocity fields are very regular. So you wouldn't expect this kind of velocity field from ongoing mergers. One more point we see is that the velocity dispersions are high, on the order of maybe close to 100 kilometers per second from the points of the H alpha line. So this is just a sample of a few out of about 100 galaxies that we have in the SINS survey. And if you look at this part of the plot, these are the rotation-dominated galaxies. These are large disks with very ordered rotation fields. In some cases, such as this one, you really see the spider diagram, which is a signature of just a differential rotation in a declining disk. So the picture we have from this is that those star-forming galaxies, or at least the bigger ones, the more massive and star-forming ones, are disks, but they're different from local disks in that they're rapidly star-forming, very gas-rich, clumpy, thick, so we see that the edge on they seem to be about 1 kilopascal thick, and turbulent in the sense that the observed velocity dispersion is of the age of large.
So are local merging galaxies not like this? Is that what you're saying?
Yeah, so local merging galaxies, star formation is concentrated in, is much more concentrated.
Rotation doesn't support the galaxy.
So the paper Shapiro 2008 compared local mergers. She simulated observing them at redshift 2, and with the same kinematical techniques, she showed that they look completely different than those large disks with orbital.
They are rotation supported, but they're most of the self-formation get kind of presence. It's much more compact. Starfall. The galaxies
also
themselves are much bigger, but the galaxies have a lot of stuff. These things have much more gas and rich stuff.
So there aren't any sort of gas-rich mergers today? Is that what you're saying?
There are gas-rich mergers in the centers of galaxies, but there are no overall gas-rich mergers. There aren't any galaxies that have that much gas.
So the ordered motion that you see, is that evidence that just evidence that a merger is not going on at that moment when you observe it? Or is it a stronger thing, which is evidence that the star formation was not triggered by it?
Yeah, well, there is discussion about that, about how quickly in a gas-rich merger the gas can resettle in a disk. So basically, I guess you can argue exactly about the time, but this means that sometime in the past, probably at least a few hundred megayears, there wasn't a major merger. So before I go into my hydro simulations, I just want to make a short comment from the analysis of the merger trees. So I just quantified the growth rate of dark matter halos, which I mentioned before, as a function. So this, the mean accretion rate of dark matter halos is 400 solar masses per year at redshift 2 for 10 to the 12 solar mass halos. This is So you see that again the evolution with redshift is very strong, similar to the evolution of the merger rate. So locally the growth rate of dark matter halos is much slower. This can already just with a very simple argument can give us a clue at how you can get such high star formation rates at redshift 2 without needing mergers as we need in the local universe. Just take this accretion rate of the dark matter halos and you assume that with some high efficiency the barriers which are associated with this dark matter go into the center of the halo, into the galaxy, in the, say, in cold mode accretion or cold streams, then you get high, so on the order of 100 or a few tens solar masses per year of star formation, which then, I mean, in the ballpark of the observed galaxies. So at high redshift, you don't need mergers necessarily to have high star formation rates, simply because the universe is much denser and the growth rate of halos is much higher.
So that's all from spoon accretion, right? Not from merger.
Right, so this is, sorry, so this is the accretion rate of non-major merging halos. So, yeah, so you get this, as I said, the resolution we have, anyway, about half the accretion is coming from really smooth accretion with no mergers at all. So if you remove the major mergers, you don't reduce much the accretion rate. Okay, so what I want to discuss now is the hydro simulations, and specifically I will try to say a few things about the clumps we see in those galaxies. So, first questions which are debated right now, whether those clumps are transient, star-forming clumps, or whether they are really massive and survive for a long time in the galaxy, orbit a few times, and then possibly fall to the center of the galaxy by dynamic friction and form a bulge. This is a scenario that was suggested in a few years by a number of authors, and there's been also discussion on whether those clumps, high star-forming clumps, or a lot of the star formation in those galaxies is concentrated in those clumps, whether they are disrupted by feedback or can survive. So I want to address these issues. So my simulations are cosmological zooming simulations in 100 megaparsec blocks on the side, where each time I focus on a different halo in this box with high resolution. The highest resolution I have right now is where gas or invariant particles have 10 to the 5 solar masses, and the spatial resolution is between 50 and 100 parsecs. I chose halos of 10 to the 12 solar masses at redshift 2 to focus on, and I chose them to have relatively quiet formation histories at redshift 2. So they haven't had major mergers with the halos between redshift 2 and 3, and they also have some not very low growth rate with halos. So in general, I take these criteria, give me 15% of the halos of this massive this redshift. So the halos I'm focusing on are not maybe the most typical halos, but also not very rare ones. This is what I have for now. So I've been running the simulations with Gadget 2 and the SPH code, and we have the version from developed by Romilda Venice group in Tucson, where on top of we have metal cooling and HEV stars, but the main ingredient of this model that I want to discuss is the model for momentum-driven super winds. This is based on the theoretical ideas from Nolan here, and also there is some observational support for the scaling here. So basically what happens is that star-forming gas, or sorry, new young stellar particles, they keep their surrounding, their neighboring gas particles outside of the gas. In the standard Gadget mechanism, where those gas particles are hydrodynamically decoupled for a short while until they go a few kpc above the disk outside of the galaxy. And what's important is the scaling of these winds, so the momentum-driven scaling, which means that the velocity, the kick velocity of those particles scaled with the escape velocity of the galaxy. But the amount of momentum per unit star formation is constant, so low mass galaxies with lower escape velocities will have larger mass loading factors. So the ratio between the mass which is put into the wind to the star formation is larger for small mass activity.
Sorry, how do you put the momentum in? Do you put it nearby with the radius?
So you just you take random neighboring gas particles around young stellar particles, and just decouple them hydrodynamically and give them a kick of a few hundreds of kilometers per second.
So is it something like this?
Yeah.
They're decoupled though, is that what was that?
And decouple those gas particles from the hydrodynamics for a period of about 50 or 100 milliyears until they're a few tens of kpc above the outside of the disk, and then they come back to the hydrodynamics. Now, if you don't do that, the effect of the wind is very well. The wind is not efficient, so those gas particles just given the kick. They will come back to the disk very efficiently just after a few kpcs. And basically, it doesn't really, well, basically it's like not putting it away. This is definitely, and this is, sorry?
These winds don't work.
Yeah, so with the resolution we have and possibly the hydrodynamical limitations of the SPH code, if you don't decouple the particles from the hydrodynamic for a while, you don't really basically by hand throw them out of the galaxy, then this doesn't work. And definitely, we discussed the paper, that's where...
That's a shortcoming of simulation, observation.
Yeah.
I think small puzzles and they get out.
Yes.
But this is why it's a subversion model.
But doesn't everyone do that?
Yeah, everybody has some version of this.
Yeah, I mean, there's
Some version of it.
there's a group from Leiden, Shay's group. They chose not to decouple their winds, and indeed what they showed is that for low mass galaxies, 10 to the 10 solar mass halos, the wind is very efficient. In 10 to the 12 solar mass halos, the wind it's a very small font.
As you increase the resolution, you're saying this problem will go away.
Observation.
Yeah, high resolution.
Talk about simulation. No, they don't have any clue about this stuff.
Yeah, I'm not
The answer is
sure.
they hope
Actually.
that they go to high resolution it would work better, yes. But it's a hope.
And the amount of momentum you positive is corresponds to the stellar star formation of the star particle, right?
Right, so basically, it's corresponds to the amount of star formation you have in the galaxy, just by the fact that each stellar particle that has just formed injects a constant amount of momentum during its first negative interval. So there's one more important ingredient of the model I want to mention is the effective equation of state of the star-forming gas. So in the, I chose not to use the widely used Springel and Turnquist multi-phase equation of state because it's very stiff. And as I show you, if I use that, basically I just cannot get clumpy gases. This is because as the gas starts to contract, it's just overpressurized and smooth. So again, for numerical reasons, I wanted to use the softest equation of state I could, as long as I still resolve the Jeans mass so that I don't have artificial fragmentation. So I'm using an isothermal equation of state that takes it okay. And when I reach a certain density, then I start pressurizing the gas with this phototropic index so that I have a constant Jeans mass which is resolved. What I want to say is that the velocity dispersion in the gas is a few tens of kilometers per second, so it's higher than the sound speed of isothermal gas we mentioned before. So actually this temperature floor doesn't really affect the dynamics of the gas. Okay, so first I want to discuss globally the role of the wind. So with this momentum-driven wind, we get first we get a very reduced n star over n halo fractions or gas formation efficiency. This is a plot of stellar mass over halo mass as a function of halo mass, and you can see that it peaks at about 10 or 15%. This is consistent with the observational constraints. If we have no wind, then we have an overcooling problem where in all halo masses, a large fraction of the cosmic share of baryons are just stars, and we have very stellar illuminated galaxies. So we also have increased gas fractions with this scaling, increased specific star formation rates or star formation rates. So this is what I showed you before. Star formation rate is a function of galaxy mass. This is the observed regime scatter I showed you before, and our galaxies lie very nicely on the elevation. And we have flat or rising rotation curves as opposed to deep rotation curves.
See what fraction of dynamics lets you go 3% of the galaxy back up?
A lot. So basically around, say, in the 20 kpc around the galaxy, about half, say, more or less of the gas has been inside the galaxy in the past and is flowing from the wind. This depends on also the mass of the galaxy.
Do you follow long enough to see, that many times you see sort of recycling where it goes out to the rear radius and then later is recaptured?
Right, yeah.
You see that as well?
We see that, yeah. And when less than what Remedial finds, because we just want to redshift 2, but this becomes worse and worse. Okay, so with the state equation of state that I mentioned, you see basically an exponential gas phase, which is smooth. But with the software equation of state, you see strong features, so elongated features or even more round clumps. This is gas surface density. This movie shows. This movie shows the gas from redshift 2.4 to redshift 2. So you see that the disk has structures, but you don't see those structures surviving very long. They're just kind of, it's all a big mess, more or less, in the disk. This shows the same thing in sort of surface density of star formation rate. So you see those clumps, here for example, they form because the disk is gravitationally unstable, but then they just disrupt. So the disk has Q, tumor Q parameter close to 1, they're marginally unstable. But those structures don't survive long, and the reason for that is the feedback. So this is the star formation timescale divided by the mass loading factor of the wind. That is the timescale on which gas is basically thrown out of the clump. With the Genel law, this timescale is actually shorter as the gas contracts. Star formation timescale becomes short, so a few hundred megayears, divided by the large mass loading factors into the mean, this time scale is shorter than the orbital time in the disk. That means that the gas is basically kicked out of the clump before the clump moves inside the disk and can replenish itself from the disk. So basically, if Q dropped to be slightly below 1 in a clump, in an unstable region of the disk, just by decreasing the surface density there, by moving the gas out, this region becomes then, with having Q over 1 and becomes stable, and this is where you see the clump just disappearing, while other clumps form in other regions of the disk.
You convinced
So
Genel of this?
Sorry?
Are you convinced Genel of this?
Yeah, so we've discussed this. We should, yeah, I mean, this is kind of a different mechanism from what happens here than what they describe. So in my simulations, the clumps never actually virialize. They're always just marginally unstable. And basically, Mark Cromos and Shai agree that if this is the case, this may well happen, but this really depends. So the shortcoming of this is that this is based on the galaxy-wide parameters of the wind, and we don't really resolve the structure inside the clump, so this all depends on this assumption. I wanted to check whether this scenario, as opposed to the scenario of sort of long-lasting clumps that fall into the center of the galaxy, whether it is consistent with the observations. So I've used the radiative transfer called sunrise to create more images of the galaxies. This shows you before snapshot before extinction, without last extinction, in the observed optical, which is the res frame UV, and in the res frame optical. So here, the res frame optical, we see the bulbs, the central concentration of stars, while here we probe just young stars, so we see the regions of star formation. After considering kind of maximal dust extinction, which is probably a little bit exaggerated, we see that the galaxy is still clumping, but the clumps are completely different than the real clumps. So basically what you see here are very mild clumps, but where there's also even less amount of gas. So we see kind of holes in the dust, kind of a combination of holes in the dust and small overdensities of young stars. This can explain the observational fact that the clumps observed in the UV and the clumps observed in the optical or in the H alpha for the same galaxy do not necessarily overlap, they're not in the same position. So if you really look at the concentration of the distribution of stars and of star formation, they're always together, both whether the clumps survive or not survive. But this differential extinction can explain why the UV clumps are actually different locations than the real clumps. While we expect the H alpha, which is in the res frame R band, to be much less effective, to correspond more to the less distinctive case of the res frame optical. So in this case, we see that there's gas again in the ring, which absorbs those clumps, and we see that the center is much more prominent. There are other cases, other snapshots in the same galaxy where there's also a large amount of gas in the center, and so the center is also extincted, and the galaxy actually appears larger after including those. So all in all, this is quite complex, and but it could be consistent with the observations. Last point I want to make is about the kinematics of the galaxies. So in my simulations, the clumps are actually minima in the velocity dispersion because they are just more denser, and the dissipation of the velocity dispersion is faster. And they are fairly massive, about 10 to the 9, so the tumor mass. So the circular velocities are up to 100 kilometers per second. But such differential rotation velocities across the clumps are not observed. And also, the clumps as minima in velocity dispersion is also not observed. But we can actually explain with the simulations why this is not observed. So these are mock images of a snapshot where we see the star formation, the H alpha, and face on velocity dispersion and edge on rotation, and we see the clumps. You cannot really see them in the kinematical features. The same is true here. And the reason, there are two reasons here. So one is that the clumps, as I said, are never virialized. So the rotational velocities are actually smaller than their circular velocities. And the second is that once you include beam smearing, so a resolution of about 8%, then some of the internal rotation translates into dispersion, which then compensates for the low intrinsic dispersion. And all in all, what I get from those mock images is very similar to the picture which is observed, and it's actually going to be published soon by Neuhaus. New signal to noise, high signal to noise calculations of the kinematics of clumps.
I'm trying to understand, like, there are things out here argue that these clumps that we observe are not associated with larger bound objects within this, because they're extinctive, they can't see them. So, if you observe these
Right, so-
in galaxies, then how is it like
Okay. Yeah, so this is in the rest frame using, where the extinction is much stronger than in the, for the H alpha, which is in the rest frame 6500. So I don't have an H alpha image here before extinction, but the extinction for the H alpha would be more or less like here, which is much weaker than here. So we don't have artificial clumps forming in the of the rest frame optical case. So we expect the H alpha clumps to be real clumps and correspond to the optical continuum clumps. But the UV clumps are maybe different, and this is also the truth is probably somewhere in between. This is I deliberately used very hard, but kind of maximum extinction that you can imagine. That using the sunrise.
You put it in the galaxy, it's not like a screen. You put it in, just put dust in with gas. Is that right?
Yeah. Okay, so to summarize, momentum-driven winds and resolution of the particle can make gas-rich star-forming clumpy galaxies, which is good. And the same feedback, which is so important for the formation of those galaxies, when this model disrupts those clumps and make them be transient, then this seems to be consistent with the observations, or at least as consistent as competing models. We may still have a bulges problem in the sense that in all images we still get, with our dust, we always get a concentration of light in the H band, because the stellar disk is more or less exponential. This is true also for models in which the clumps do survive for a longer time, while some observations in the H band of galaxies, some show really no concentration, so very clumpy galaxies with nothing at the center. So we may still have something that we don't understand there. Yeah, so I'll stop here. Thanks for everything.
Yeah, so in your zoom-in thing, you took, like 15% of the 10 to 12 solar mass halos. So could you comment on what you think, what you might guess the other 85% are doing and how they would look like compared to the observations?
Yeah, so one of my points here for what I'm going to do in the near future is look at more representative sample of halos. Well, some of them, in reality, some of them are quiescent. We know that we have compact red galaxies at redshift 2 that are less abundant than the star-forming ones, but some of them should be like that. And it's actually a good question whether we can form such objects with this model. Also, we have mergers. Some of them will be ongoing mergers. Some of them may be the more dispersion-dominated galaxies, which are in this part of the plot. I have to focus on that. So we see also a population of galaxies where the velocity dispersion is, say, 100 kilometers per second, and the rotation velocities are similar or even less than that. So it's still really not clear what this population is, whether it's small mass galaxies or less, or just more compact ones. Maybe just edge-on ones, we don't really know. So,
Do we try to do any major mergers?
no.
Because those things look like major mergers, right?
Yeah, that's an option. Yeah, so I hope I can tell you more in a few months.
Any other questions? Okay, well, maybe it's something